gas laws. But our lesson will be started from the experiment. Can crash experiment. I think you would be interested in that experiment. Let's start. And how do you think? Why does it happen?
I think when we put the can inside the water, the air aimed to cool, the gas cools, then that's why the gas aimed to shrink, and this shrinking made can to change his shape.
What do you think are the main learning objectives of today's lesson?
Maybe the relationship between three state variables like pressure, volume, and temperature.
Can you write it down on the blackboard, please? E.
Describe behavior of molecules in ideal gas.
Yes, and you can write it down. Так. Thank you for sharing your ideas. And now we are going to list our learning objectives. I think some of them are related to your explanation of an experiment. First learning objective of our lesson is describe model of ideal gas. Second one, describe changes in volume due to pressure with a constant temperature. Describe changes in volume due to temperature with constant pressure, and finally, plot and analyze graphs of isoprocesses. You've prepared your home task about behavior of ideal gas. Two pairs. First pair prepared information about differences of ideal and real gas, and second pair prepared information about temperature and pressure of an ideal gas. This will be very helpful to our future explanation of isoprocesses.
We prepared a video presentation about differences between ideal and real gases. So there are some key features about ideal gas. The particles of ideal gas extremely small, and where its mass is almost zero. The second one is the collisions or impact between the particles are elastic. And finally, infinitively compressible.
In comparison with ideal gas, the real one really does exist in our world. First of all, the real gas has small attractive and repulsive forces between particles. And second of all, collisions between particles are inelastic. And when the particles collide, the energy is lost. Particles significant compared to space between particles, and the interactions between particles are insignificant.
The next one is ideal gas conditions. There are two of them. So the first one is high temperature and the second one is low pressure. Particle size small compared to space between particles, and interactions between particles are insignificant.
Right, please.
I'm going to talk about temperature in ideal gas, and we should remember that it's proportional to average kinetic energy of the molecules.
Thank you. And Alina, please, about the pressure.
Pressure is caused by collision of molecules on the walls of container, and the pressure is higher when there are many collisions committed, and respectively lower when the molecule gas collide fewer times.
Thank you. As you said before, there are three state variables like pressure, temperature, and volume that defines state of the gas in general. Now we are going to find the relationship between them, and you will use computer models in your notebooks. All of you have links on your desktop. Please open your notebooks, and now we are going to investigate gas laws. Thank you for your active participation in this activity, and now I ask one representative from each group who will show their results, make conclusion about their experiments. Please, Aina.
The process of our group is called isothermal process. This process means that the temperature stays constant while the pressure and volume change. Here we can see that when we change the volume, when we decrease the volume, the pressure increases. So the relationship between volume and pressure is inversely proportional. It means that when the volume is decreased, the pressure increases. It can be explained by the law of Boyle-Mariotte. It states that for a fixed amount of an ideal gas at a fixed temperature, the pressure and the volume are inversely proportional. So the gas molecules hit the walls more often when the volume is decreased. That is why the pressure bigger.
Thank you. Lani, next, please.
The process of our group is isochoric, and it is one type of thermodynamical processes where the volume is constant. In other words, the relationship between pressure and temperature is directly proportional. And as you can see, the line graph is straight, and as you notice, the pressure not starts from zero because it occurs only when temperature is equal also to zero.
Thank you.
In the graph, we see isobaric process, and in this process, pressure is constant, so volume is directly proportional to the temperature.
Thank you. Nikolai?
Did you notice that the graph doesn't start from origin? What would happen if we will extrapolate graph to zero, absolute zero? What is the definition of absolute zero? As we remove heat from a substance, its temperature drops. The particles of the substance move slower and slower, and finally will reach a temperature at which all particle motion almost stops. The temperature is called absolute zero, and it's the lowest possible temperature. Molecules never become absolutely motionless, but the kinetic energy is so small, it might be as will be zero. The temperatures of everyday objects are only a small part of the wide range of temperatures present in the universe. Temperatures in the range are from just above absolute zero to more than 10 to the 10th power Kelvin. Temperatures do not appear to have an upper limit, but there can be no temperature less than minus 273.15 Celsius, which is called absolute zero.
Thank you for sharing your results. And now these three laws can be combined in one more general relationship about three variables, between three variables. And as you said before, the first process is occurs when temperature is constant and called the isothermal process, at the thermal process, and the relationship between two changing variables, between pressure and volume, can be written this way. As you said, pressure and volume inversely proportional to each other. Second one, isochoric process, when the volume of the gas stays the same. Relationship between pressure and temperature is directly proportional. And this third law, when pressure stays constant, we said that volume and temperature directly proportional to each other. Now we are going to use these relationships, these laws, in the problem solving. We have several problems to solve, and let's start from the easiest one.
That this process is isothermal because temperature is always constant and our units are not in the international system. Then here we convert it. Then we just do not include the temperature in the formula and we get this expression, and this is the answer.
is equal to atmospheric pressure. Also know that pressure of Earth is constant on the surface of Earth, and we must calculate the minimum pressure. We know that we have other processes in this problem, and it means that we can use this expression. Here, as a consequence, we can write that the ratio between volumes is equal to the n, and it is equal to the ratio of first pressure and final pressure. And from these expressions, we can conclude that we can have the system of equations. By uniting these two expressions, we can find the meaning of depth. The meaning of depth is equal to n minus 1 multiplied to the final pressure and divided by multiplying of density of water and gravity. Density and gravity are constant, and final pressure is constant too. So it means that in final we can have these expressions. We can put any number, replace n by any number, and we can have the answer. Если он будет кривой, ничего страшного. Цифры только эти буквы покрупнее, ПВ и так далее. Хорошо.
So we are given the graph which shows the relationships between pressure and volume, and we are going to analyze it in the different points. First of all, in the points from 1 to 2, the pressure is increased and the volume is constant. From points 2 to 3, the pressure is decreased, volume is increasing, and because of because this graph shows the isothermic process, the temperature is constant. Then from 3 to 1, it will be constant pressure and decreasing in volume. And we are going to draw it in different ways in the graph of that will show there is a bar and is a whole process. And now we are going to draw this graph in the different relationships. First of all, it will be pressure against the temperature, and the next one it will be volume against the temperature. this relationship in the different type of the graphs. So here is the common style of relationships between free state variables, and from difference graph we are going to we can represent it like this. First of all, in the from 1 to 2, because of constant volume, this equation will look like this. It means that relationship between pressure and temperature is direct proportional to each other. It means when pressure is increasing, temperature is also increasing. We can see it in this part of the graph. Second one, we can see that here is constant temperature. It means that this is the isothermal process, and it will look like this. Here is the inverse proportional relationship between pressure and volume. It looks like this in the first graph. The next one, we can see that here is stable variable is pressure, and the graph look like this. It means that here is also direct proportional relationship between volume and temperature, and here we can see it in this part of graph.
So the main task of our experiment is to measure the changing of the volume of air in this LMAF flask, and during heating it at a constant pressure. And this pressure has to be equal to the surrounding pressure.
So at the first time, we should measure the initial temperature of water. So we will use thermometer. Now we saw that it is 23. Okay, you're right. 23. After this, we should heat the water. As you see, the volume of water is increasing by the comparing with initial state. It will happen until the water will heat it.
By using our data on this table.
In isobaric process, the pressure is constant. That is why the volume is direct proportional to temperature. And now we have in graph we have straight line.
So now we have plotted a graph by using our data on this table.
So in isobaric process, we have constant pressure. That is why the volume is direct proportional to the temperature. And now we have straight line.
there is a gas, and the initial characteristics of gas are given. It's a pressure and volume. This gas expanded, so it's expanded isotomically. The temperature during this process remained constant. And also we know for how many liters it changed, so how the volume has changed. And the problem is to find out what was the temperature in all process. And we know also the given concentration in the final state of the gas. So the gas expanded isotomically, and there we know that if temperature didn't change, it was the law. We can solve this problem by the law of Boyle-Mariotta. Boyle-Mariotta, yes. And the equation is sounds like the multiplication of initial pressure and initial value is equal to the multiplication of final pressure and final volume. From this formula we can rearrange the value of the meaning of final pressure, so it's multiplication of initial pressures and value and divided by final value. We know that final value is equal to initial value plus the changes of value. Why? Because the gas expanded. Yes. So in the place of final volume, we can put the sum of initial volume and change in the volume. And we also know that the pressure of the gas is equal to its concentration in final state, multiplied by Boltzmann's constant and by its temperature. So from this equation, last equation, we can rearrange our final value of temperature. So the temperature is equal to multiplication of initial volume and initial pressure divided by final volume and concentration and Boltzmann constant. There we can put our given meanings, do all our calculations, and at the last we can explore that the temperature was 333.6 Kelvin.
Thank you for your problem solving. And now just talk about the application of isoprocesses. How do you think where we can see processes in which some of the state variables stays constant, such as isothermal or isochoric processes? How do you think?
I know one example of isobaric processes, which is taken from a real life. So when we put the air into the cylinder in which the piston is moving free, the volume of cylinder will increase at the time when pressure will be the same.
So now we have considered what is it isoprocesses are, and here we have questions where we can see it in the real world. As example, can be car. When it's moving, the tire of the car is changed in pressure of the molecules inside and the temperature because of the friction force, while volume is stayed constant.
Thank you, Scott.